Alrighty, so we're going to start looking at translational to rotational motion. And translational motion is the idea that an object is moving this way. So not worrying about if it's rotating at all, just how fast is it going side to side. And that's what we did in the first chapter of the book, is we looked at objects falling or objects moving or cars driving, and we didn't care about anything rolling. All we cared about was how fast the actual object was moving in its entirety. In this chapter, we're going to look at how fast it rotates and the relationship between the two. So if I have this ball start rolling without slipping, you will notice that there is clearly a relationship between how fast it rotates and how fast it moves sideways. The faster I have it rotate, the faster it would also move sideways. And if you notice, this little dot on the bottom that started at the bottom is now at the bottom again. And so there should be a relationship between how far it went this way and the fact that it rotated around once. And it makes sense that that would be the circumference. So if I look at the circumference of the circle, that's how far it should have rolled, because the circle didn't slide at all. It was just rotating. And of course, assume that my circle was staying the same dimension the whole time. If it is true then that it rotated one circumference, I'm going to talk about that as well. The distance that it traveled this way. It also rotated a certain angle here. And I know that it traveled a distance of whatever the circumference is. So if I say that the distance it traveled is equal to 2 pi r, which is the equation for circumference, then I'm going to also notice that I could rewrite this as how far it went is equal to, remember how I was talking about that angle? Well, the angle in radians is 2 pi is equal to 360 degrees. And so this 2 pi is how far it rotated as it went one whole circle. So this is actually, instead of being 2 pi, this is just the angle that it rotated in radians, times radius. And because v's and lowercase r's are so similar, I'm going to write this as an uppercase R. And there I have it. This is my actual equation to go between how far it went and um, and the rotate, like how much it rotates. So if I had it rotate 1.2 radians as that angle here, then I could figure out how far it would have rolled. Or vice versa. Maybe it rolled 1.2 meters, and I then could figure out the angle that it has rolled, assuming that I know what the radius of this circle is. So let's take that one step farther. If I know something about position and angle, I'm going to also be able to tell you something about velocity, because position or change in position divided by change in time then should be somehow related to the change in angle divided by its change in time. And all I'm doing then is on both sides of these equations, I'm just dividing by time. So if I take this and I go position divided by time, or change in position divided by change in time, is equal to my change in angle divided by my change in time, then this is still the same equation on both sides. But now instead of it being this, I'm going to call it velocity. And on the right-hand side, if I'm looking at how my angle changes over time, then that would be my angular velocity. And so this omega is angular velocity times r. And then I could do the same thing again. I could divide by time on both sides. And when I have my change in velocity divided by my change in time, I get acceleration. And when I have my change in angular velocity divided by my change in time, I will get angular acceleration. And so what I end up having is I can make a very simple table to convert between the two. So I can say, okay, well, position or how far it has rolled is equal to that angle that it rolled times my radius, or my velocity is equal to my angular velocity times radius, or my acceleration is equal to my angular acceleration times radius. Now, of course, I could also rewrite these and put them in the other way, and I could say position divided by r is equal to angle, and I could say velocity divided by r is angular velocity, and I could say acceleration divided by r is equal to angular acceleration. And all I'm doing is just dividing both sides by r. But it really doesn't matter. To me, this way makes more sense to memorize. If you like this way better, it really doesn't matter. You will be able to do everything the same way. So that's how you get this. So this is important. You'll want to memorize that or write it down or have a way of remembering it. My stupid way of remembering this is I like to think of it as here's my circle. And as it rotates, this angle theta, and here's r, and then my distance around the outside is x. I like to think of it as the two on the inside multiplied together give me the outside thing, because that's, I don't know, that's just the way I think of it, as the two on the inside equal the outside. So then I have r times theta is equal to x. And then I know that I can do the same thing with velocity and acceleration. So the way that I remember this is I just remember it by drawing the circle. And then that's the easy way that I remember it. Whatever way works best for you is great. If you're a memorization person, awesome, congratulations. I'm not. But whatever works for you is great. All right, so that's how you convert back and forth. So when you have something in angular and you need it in linear or translational, or if you need to go the other way around, that's how to do it, is you can just use these conversions. But if you're just trying to figure out how far something has gone, then you're going to want kinematic equations. So going back and remembering our kinematic equations from the first chapter, this is what you had. And just now we talked about what these equivalent rotational things are. So instead of position, when we talk about rotational stuff, we're going to be using angle. And this is just your angular position. And this will be your angular velocity. And then angular acceleration looks kind of like a fish. And then time is going to be the same. And it doesn't matter if you're talking about translational or rotational. They're both going to have the same time. All right, so why does this matter? Well, it matters because when you look at these kinematic equations, now all I need to do is plug in these other variables, because all of the physics is exactly the same. So the equations are the same. So instead of position, I'm going to put in angular position. Instead of starting angular position, I'm going to put in, instead of starting position, I'm going to put in starting angular position. Instead of starting velocity, I'll put starting angular velocity. And then time, and 1/2. And then instead of acceleration, it's going to just be angular acceleration. And then time is the same again. And then that's it. That's the same equation that you've used since chapter 1. And then I'm going to do the same thing with the other two kinematic equations. Instead of velocity, I'll put angular velocity. Instead of acceleration, I'll put angular acceleration. Time is the same. Instead of velocity, I'll do angular velocity. And then I just keep going with that. And then that's it. So honestly, the reason why you won't be given these red equations is because you already have the black ones. And if you have the black equations, then you know what the red equations are going to be, as long as you know that instead of velocity, it'll be angular velocity. Instead of acceleration, it'll be angular acceleration. And you have to convert all of them. You can't just convert some because they're not equal to each other. But you can figure out one if you have the other using these things up here. All right. So the last thing we need to talk about is an object that is rolling without slipping, which is a little bit weird. So we're going to have another circle again. All right, so I'm going to go ahead and draw the ground here. And what I'm going to do is I'm going to attempt now to roll this without having it change sides or slip. So just go with me on that. And I want you to pay attention to how fast these dots are going when they touch the ground compared to the ground versus the dot on the top, how fast it's moving relative to the ground, and then also the middle dot, how fast it's moving relative to the ground. So as I rotate this, you probably should notice that up at the top, it moves fast. And when it's touching the ground, it's basically not moving, right? Because if it was moving when it touched the ground, then it would be slipping. And so I want to talk about what's happening for each of these things because it's one of those really common physics questions. So at the top here, it's actually going really fast. It's actually going to be going double the speed. So whatever the velocity of this thing is moving, let's say the middle of the circle is moving this way with some velocity v, the top of the circle is going to actually be rotating with 2v, because not only does it need to keep up with the circle, but it's also moving itself and rotating forwards. And the bottom of this, the velocity will be 0 because it's rolling backwards at the same time the thing is moving forwards. So let me just kind of try to explain this one other way. If I have circles again, so let's have another circle here. And I'm going to talk about it just as it is moving first. So translationally, translational is just like if it was a car driving. So all three of these spots are going to be going this way with the same velocity. If it was sliding along the ground and not rotating at all, they would all have this velocity v. Now, if I talk about it just in terms of rotation, if this was not touching the ground and it was just spinning in the air, what would be happening? Well, if it was spinning in the air, then this would not be moving. This velocity would be 0. At the top, it would be going that way with some velocity v. And the bottom would be going that way with some velocity v. All right, so how do we get this thing on the left? Well, if I add these two together, what you'll notice is that this velocity goes forwards and that velocity goes forwards. And so if I add those two together, I get 2v going forwards. And here in the middle, the velocity is just v, and here the velocity is 0. So 0 plus v is 0. And then on the bottom, this velocity is going backwards because as it's spinning around the middle, the bottom of this circle is going backwards. But in terms of the translational, it's going forwards. And so these are the same. So it's almost like a plus v and a minus v. And so that's how they cancel out to equal 0. So you can think of it either as how it looks when it's rolling, or you can think of it as these translational plus rotational. We're going to do a lot more with these rolling without slipping kind of things. But this is one good thing to know, and just add to your notes for now. If you have any questions, let me know.